Bismillahirrahmanirrahim. So welcome to week 13, and the topic is sequential logic. So we have discussed combinational logic design, and now we are going to the next part, which is sequential logic design. Now these slides are from course called 6004. This is basically an MIT course, computation structures. This is a very interesting course. You can go and check other materials from this course. So for this set of lectures, I am not using the book slides because I find it simple to discuss with this set of lectures. We will go to the book slides once we finish with these, so that I want to clarify your concepts with this set of lectures, and then the book uses slightly different notations, so we will quickly go over the book slides so that you become familiar with the notation used in the book. So let's see, until now we can build what is called combinational logic, but if you are given a problem like the one here, which says that you have a system which has a button. So when the button is pushed, imagine you have this button, and this button we have connected a bulb. So when you push this button, okay, it should turn on the light only if the light is already off. But if the light is already on, it should turn it off. Now what is different about this problem is that we cannot solve it with combinational logic, because we need to know the state of the bulb. We cannot solve this problem until we know what is the current state of the bulb. Is the bulb off or is the bulb on? Okay, so this kind of logic is called sequential logic. It has a memory, or what is called a state, and the pushing of the button is an event. So there are two new things. One is state and the other is event, and we need to incorporate these two new functionality into our circuits to solve this problem. Now this is the general model of sequential design. So you have a memory device which works on a load signal. So if the load is for example 1, whatever is at the input, it goes to the output, and then you have this combinational logic, which is represented as a cloud, and the combinational logic has two outputs. One is the new state. So the output coming from the memory is called current state, and the output produced by the combinational logic is called new state. And then we have another output which is just simply called output. Okay, so this problem can be solved with this model. For example, this new state of the bulb, this may be the bulb state. It depends on the current bulb state, which is stored in this memory device. So previously, if the bulb is off, this will be off. And when you combine this with the current input, so if the current input is a push of the button, then your next state will become on, which is again stored in the memory device for the next cycle. So you see there is a feedback. Okay, so this is a model for our sequential logic. So our sequential logic will have feedback. So feedback is a very important idea. So we need storage, and storage comes from feedback. So combinational logic is stateless, but to build devices with state, we need circuits which can store. So there are several memory devices, for example, ROMs or RAMs, or others are latch and flip-flop. Okay, so there are so many other options which stores information, but here we are discussing the ones that can store. Let's start with the ones that store a single bit of information. So in order to store information, we can use, the first option is to use capacitor. So what you can simply do, you have this word line which is connected to the gate, and you have this bit line which is the bit that you want to store. So when you want to store a bit of information, you turn the word line on. So you apply a high voltage to the gate, and you apply your bit here. So this 0 bit is stored on this capacitor. Okay, but the problem with capacitor is that the capacitor can leak over time. So you have to refresh this circuit several times in order to store the information reliably on capacitors. Now this is how DRAMs are made. So I hope that you all know what are DRAMs. The memory that you connect to your computer. So you say 4 gigabyte or 8 gigabyte of memory. So that memory is your DRAM. Okay. Now a capacitor has this one good property that they are very small to manufacture. So they take very less area. So that's why DRAMs can be manufactured with a huge density, and the cost per bit is very low, because you can easily manufacture the capacitors in large quantities. The downside is that it's leaky, so you need circuit to refresh it, and it has some nice problems, and the interfaces are complex because the rest of the circuit is the digital circuit, which has the flip-flops and gates and everything, and here you have a circuit that is purely a passive device. So there are some complexity, but this is one option to store a single bit of information, to use a capacitor. Then the next option is, but obviously you use this information outside your computer chip. So DRAMs are outside your computer chips. So if you want a memory inside your computer chips, they are not suitable for capacitors are not suitable to be on chip with the processor. Okay, so the other option which can be useful on chip is to use the gates. So let's try to build a single bit of memory using NOT gate. So here we have two NOT gates. If you gave it an input of 0, the first NOT gate will convert it into 1, the second will convert it into 0, and you see there is a feedback. So imagine if there are switches like here. So if you have switch here and switch here, so you can control when you want to take the input and when you want to take the output. So for example, if you want to give it, so let me use it like this. So here you have a switch. Whenever you want to store a new information, you close the switch, apply the information here, and the information is then trapped. And when you want to read the output, you close the switch and read out the information. Okay. Now let's try to understand it from a voltage curve perspective, how the information is stored. So imagine this is you have this green curve, which is the curve for a buffer. So this is the voltage transfer curve of a buffer. Remember that the voltage transfer curve of a NOT gate was something like this. Okay, so the NOT gate was something like this, and if you combine two NOT gates, then you get a buffer. So the buffer has exactly the opposite characteristic curve of a NOT gate. Okay, so this is the curve of two buffers. And what about this one, this line? On this line we have Vin is equal to Vout, and this line is basically this red line that I am drawing. So on this line we have Vin is equal to Vout. So the solution of this circuit are 3 points, 1, 2, 3. These 3 are the solutions of this circuit. Now in 2 out of these 3 are stable. So this one is a stable 1 solution. This one is a stable 0 solution. But we have a solution that is called metastable. Okay, so this is the middle point, and this is unstable basically. So if your circuit goes to this point, so this may be a voltage in the forbidden zone. Remember the forbidden zone from the very first lecture? So these voltages are in the forbidden zone, and your circuit will not recognize it as a valid 0 or a valid 1. So this is a problem. Okay, so this is very important concept of metastability. And remember that the initial computers back in the early days, they used to hang a lot. So this one of the reason of a computer to get hanged is metastability. So your memory element inside may go to this central point, and when you go to the central point, your gate is basically confused to treat it as a 1 or a 0. Okay, so that's one of the things that can happen to feedback based memory elements. Okay, let's build another solution, because the one with the NOT gate does not have a gate signal. This is called gate signal. So let's try to build a memory device which can store a single bit using a 2x1 mux. So this is a 2x1 mux. So this is the select line. Now the select line, we call this select line gate. So when the gate is 1, what happens that whatever is at the input goes to the output, which is called Q. But what happens when the gate is 0? At that point, this input is selected, and when this input is selected, we have this feedback loop. Okay, and as I told you that if you want to store information, you need a feedback loop. So this is another design which can give you the property to store a single bit. Now this is called a D-latch. Okay, this is called a D-latch, and let's say sort of truth table of a D-latch is this. We have G as input, D input, and this point is our QN, and this point is our Q out. So when G is 0, so the gate is closed. We call this whenever G is 0, we call this memory state. Okay, so when the latch is in memory state, whatever is on QN appears on Q out. But when the latch is transparent, this is called transparent mode. So memory, you can call this memory state or mode, and similarly transparent state or transparent mode. In transparent mode, the gate is 1, and whatever is on the D input, it passes to the Q out. Okay, so let's try to understand it better. So on top we have the D data input, and you see here the data input is changed. So this X shows that it is changed here. Then we have a value which is V1. Then it changes again here, and then we have another value V2, and then there are some changes here. So let's see what happens to the gate. So the gate is 1 all the way, and it changes at this point. Okay, so whenever the gate is 1, whatever you have on the D is on the input. So you see that here our input is changed, so our output also changed, but after a certain amount of time, that is called TPD, which is our propagation delay of the mux. So it is basically the propagation delay of the D there to go from here to here. Okay, then again there is a change here. This change will again propagate in TPD time. Okay, so whenever G is 1, Q follows D independent of Q prime. Now this is called Q prime, and this is called Q. And when G is 0, Q holds Q prime independent of D. But what can happen, there is this small detail. A change in D or G contaminates Q, hence Q prime. How can this possibly work? What is meant by this point? This is very important to understand. Imagine if you are changing, let's say if you apply a value V2 here. Okay, so you want to store V2, and before V2 propagates to this point, okay, before V2 reaches Q, in that point, in that time, duration of time, you also change G. So what is happening? While V2 is moving from D to Q, you have changed the value of gate. So the gate is moving from transparent to memory mode while V2 is in the flight. Okay, and you want to store V2. Now this is not good, because if you want to store V2 reliably, you should not change D and G at the same time. Okay, so let's try to understand how can we do it. So let's try to build this truth table again in more detail. So when you have G1, so whenever G is 1, the latch is transparent. Whenever the G is 0, you are in memory mode. But you see, there is a very, very interesting case that is between these two states, and that is whenever D and Q are equal, D and Q prime are equal. Okay, this is very interesting case. Whenever you have D and Q prime equal, at that point the value of gate is don't care. It is like this: you want to select between two things, but both the things are equal, so it is irrelevant what is the value of G or gate signal. Okay, so what that means is that if you operate this D latch in this fashion, that you follow this sequence, you go from here to here and then from here to here, okay, then the problem of reliability will be solved. Okay, what that means is you will not change G and Q at the same time. Okay, so this is a cycle. You always first make G1. So this is the first step. You enable the latch to be transparent and enable the signal to propagate to the output. Okay, then you wait for enough time so that D and Q prime becomes equal. Now the first step is like this: first you wait for the signal to go here. This takes a time which is called TPD. In the second step, you wait for Q prime and D to become equal, and how that can be guaranteed is that you wait another TPD, this red one. Okay, so if you wait for 2 TPD, you will ensure that the value of gate is now don't care. Okay, so this is our second step, and in the third step you make G0. So you take the latch from transparent mode to memory mode. But remember, already 2 TPD time has passed. Okay, now this 2 TPD time, this is called setup time, T setup. This is very, very important. T setup is equal to 2 TPD. 1 TPD from D to Q, another TPD from Q to Q, from Q to Q through Q prime. Okay, so this is 1 TPD, this is the second TPD, and both these TPDs are called T setup. Okay, so if you want the latch to reliably store whatever you want to store, you should apply that. Okay, so you should apply that information before the clock edge. So here is your clock edge. You should apply that information before the clock edge. How much before? At least 2 TPD. At least 2 TPD time before the clock edge. Your information should be stable. Your information is not allowed to change during this time. Okay, not allowed to change. If you change, then it is not guaranteed that your information will be stored. Okay. Similarly, after your clock edge, you are not allowed to change your information for another TPD. So remember that this was the first step, this was the second step, this is the third step. So in the third step, what you have done, you have taken G from 1 to 0. Now this information will propagate. Let me mark this with another color. So this information will propagate along the circuit. Okay, and again this will take another TPD time, the green. So during this time, you are not allowed to change D. Okay, so there should be no point in time in which G and D are changed at the same time. G and D should not ever be changed at the same time. But before the clock edge, D can be changed before 2 TPD or T setup time, and after the clock edge, it can be changed when the whole time is passed. So this is called the dynamic discipline or the timing discipline, and this is very, very important. So T hold is equal to 1 TPD, T setup is 2 TPD, and T hold is 1 TPD. Okay, again let's put our latch, which is this one, in this design. Remember the problem that we want to build a push button and a bulb system. Okay, imagine if we put our device here, and here we have our combinational logic, then what can happen? Let's say we make G equal to 1, so our gate is now open, and this is the current state which is stored in our flip-flop is off. So depending on the push button, let's say the push button is 1, it will change the state from off to on. Okay, this on will come here, it will change the off to on in the next TPD, and because G is 1 for a longer time, G may be 1 for a longer time, this information will again be flipped from on to off. So you see there is a problem. We need to make G equal to 1, okay, for accurately 1 cycle. If we make it 1 for more than 1 cycle, so the latch will be open for a lot of user cycles, and the bulb will change the state multiple times. Okay, so we have this kind of combinational complete path or cycle. Okay, so our problem is not solved. Now let's see how to to avoid the combinational paths. So this is an analogy of a toll plaza where you have to pay the taxes. So imagine that the first car has paid his tax and the gate is opened. The first car can go, but what happens that all are trying to steal the tax money and they just go through it. This is an example of the combinational loop that we have discussed, that the value of G, so imagine this is our G, it is 1 for a long time. It should have dropped down when the first car has passed, but it is 1 for a long time and multiple cars were able to escape. So same is the example of our circuit, that G is 1 for multiple iteration and multiple input values were able to pass, resulting in the bulb to change its state multiple times, which is undesirable behavior. So an analogy is like this, that instead of one gate, now you have gate 1 and gate 2. So imagine the first car goes into the two gates, between the two gates, and the first gate is opened for the first car, it goes away, then this is closed, then the next car is let inside, so the gate is opened, then it is closed, then it is opened, it pay tax and go outside. So this two-gate strategy can be used to disable people who have tried to move away without giving any taxes. Okay, so this is sort of a simulation of how it works. The same, based on the same principle, we can design what is called an edge-triggered flip-flop. Now, an edge-triggered flip-flop is basically a combination of two D-latches. One is called master D-latch and the other is called a slave D-latch. The important thing to note is that both the gates are connected to a clock signal, okay, but the master is connected to the clock signal with an inverter. Now what happens that this device has very interesting features. Okay, if you want to draw the symbol for this, it is like this, that we have a D input, a Q input and a clock. So all this is inside this, and this is called a D flip-flop. Now at any point in time, there isn't a path from D to Q. There is no path directly from D to Q. If the master is in transparent mode, the slave must be in memory mode. If the master is in memory mode, the slave must be in transparent mode. Both the master and slave are never in the transparent mode at the same time. Okay, so this is very important to understand. Now, if you draw the sort of timing diagram of this signal, so you will see
there is some. So here is the D signal. Okay, so I just will remove it. So here is the D signal. Here is our clock signal, and then we have this star node, which is the node between master and slave. So it is basically the output of master and the input of slave. So what happens when clock is equal to, when clock is 0, okay, so the master, when this is 0, the master is in transparent mode and the slave is in memory mode. So at that point, whatever is on the D, it appears on the star node. So you see, from here to here, from here to here, the star node is exactly the same as D. But when the clock is 1, the star node retains its previous value. So its previous value was 1 here, so it retains its previous value. Again, when the clock becomes 0, so in that interval of time, star and D are equal. Again, when the clock becomes 1, it keeps its previous value. So its previous value was 0, it keeps it. When the clock becomes 0, it again follows D. So this is the life cycle of the star node. If we look to the output Q, it will follow the star node because star is input to the slave, and it is working in the reverse order. So whenever the clock is 1, the slave is transparent and the master is in memory mode. So you will see that it is 0 because the clock is 0, so this is some previous value. Whenever the clock is 1, you will see the star node being copied to the Q. Again, the clock is 0, so the star node value is neglected because at this point the slave is in memory mode. Again, when it is 1, the value of slave is copied, the value of star node is copied. Okay. Again, the clock is 0, so it goes to the memory mode, which says that the value of 0 should be kept. Now, a very interesting effect is that if you look to this whole thing, you will understand that it is working on positive edges. So it is sampling the value of D on the positive edge, and it is bringing that value to the output. It is sampling the value at the positive edge and bringing it down, to the output. Okay, so this is very interesting. There is nothing inside this circuit which can detect the positive edges, but just by intelligently combining two D latches in the master and slave configuration, you are able to achieve something that works on the positive edge. This is very interesting. Okay, but there is something that you should be aware of on the star node, and this is very important. And which is this point. This point says the accumulated TCD through the accumulated contamination delay through inverter, this is this inverter, and G to Q, which is this point of the master, must cover the whole time of the slave for this design to work. What it says is that the contamination delay of master should be greater than the hold time of the slave. What if I explain it in simple English? It will say something like this: TCD is the old value. So the old value of the master should be there for an amount of time which is greater than the hold time of the slave. If this condition is violated, the whole circuit will not work. And this is a very, very important constraint. So, summarizing, we have these 4 timing constraints on our memory elements: TPD, TCD, TSetup, and THold. Okay, and then these, if we consider a single clock synchronous discipline, which says that if this is your whole circuit, and if this whole circuit, this is our cloud 1, cloud 2, cloud 3, cloud 4. So this may be a complete microprocessor, and for example, this may be cloud 1 may be an ALU. So the output of ALU goes to a register. This is a register or memory element, and basically register and flip-flops are the same thing. A flip-flop is a single bit register. When you have multiple bits, then you don't call it flip-flop, you call it register. So a register is a multi-bit flip-flop. So for example, this may be ALU, this may be your floating point unit, and all are connected in a way that you have some cloud where computation happens, then you have the storage, then again another computation, another storage. So whole of your circuit can be designed in this fashion. So this is called single clock synchronous discipline, and all of your flip-flops are connected to the same clock. So this is one way to design circuits. You can use multiple clocks, that is also possible, but it becomes complicated to synchronize these clocks. Okay, so for the single clock synchronous discipline, the timing detail is something like this. We have 2 formulas which are very, very important. One gives us the maximum frequency of a circuit, and the second gives us if our circuit will ever work. So this slide is very, very important. So let's first consider what is the maximum frequency. So this is our model, okay, which we have a register R1, we have a register R2, and between these 2 registers we have our combinational logic CL1. Now what happens that the flip-flops, this is flip-flop 1, flip-flop 2, the flip-flops works on the positive edges. Okay, and what should happen between 2 positive edges? So if I consider a positive edge like this, let's say this is our positive edge. Okay, this is our first edge, this is our second edge. So what should happen on the first edge? Something like this should happen, that our input, which is at D, should go from here to here. Now the amount of time that it takes is called TPD. That is called TPD of R1. Okay, then after that this data should go from here to here, and the amount of time it takes to go from here to here is TPD of CL1, which is combinational logic. Then here our clock edge is coming. Remember that our data should be stable. before the positive edge. So it should be stable before the positive edge, at least t setup time before. So our clock period, this is our clock period. Our clock period should be long enough that these three things should happen. So which means that our clock period is greater than equal to TPD R1 plus TPD of combinational logic plus T setup of register 2. This is a fundamental equation that gives us the maximum frequency. So this gives us the period, and you can convert the period to frequency. So this is a very important formula if you want to know the maximum frequency of your circuit, and this circuit can be a whole microprocessor. Then you need to locate two registers such that the combinational logic between these two registers should have maximum TPD. If you take two registers between which you have the maximum TPD, then that path is called critical path. This path is called critical path, and the maximum frequency is dependent on the critical path of the whole system. So this is one equation which is given by this T2 but slightly rearranged. The second equation that we have talked about is this one that in order for this circuit to work, the contamination delay of R1, which tells us for how much time the value at the output of register 1 will remain old, plus TCD1, which tells us for how much time the value at the output of combinational logic will remain old. So these two combined should be greater than the whole time of register R2. If this condition is violated, our circuit will not work for any frequency. It will not work for any frequency. So this is our equation 1, this is our equation 2. If equation 2 is violated, what you can do, you can, it's very simple, you can just reduce the maximum frequency of your processor or your circuit. You can say, okay, let's not connect a crystal of 100 megahertz, but let's connect a crystal of 50 megahertz. So this is something that is in your control. But equation 1 is very, very important. If you sort of violate equation 1, your circuit will not work for any frequency. So if you are interested, here are some questions. If you are interested in answering these questions, you can think over the things that I have talked about. So for example, how much time for useful work? So this is basically asking about the TPD of CL1. So how much time? It is basically equal to T clock minus T setup. Okay, these are in your, this will give you the maximum amount of time you have for combinational logic. So here is, for example, an example. You have this model TCDR of R. So imagine in the previous slide we have two registers. So this was our model. Okay, sometimes this model is called RTL, register transfer logic. Okay, so then this is very important term that is used in industry. So this was our RTL model, but it is also like this, that if you have combinational logic and instead of two registers you have a single register with feedback, the model does not change. So you see, again, this is RTL model, and you are given the continuation delay of R1 is 1 nanosecond, propagation delay of R is 3 nanosecond, setup time is 2 nanosecond, hold time is 2 nanosecond. For combinational logic, what should be the value of TCD if TPD is this? So you have just two formulas, and you can, for example, from the equation 1, the TCD of R plus TCD of L, which is combinational logic, it should be greater than T hold of R. So if you plug in the values, TCD of R is 1 plus TCD of L is unknown, it should be greater than T hold, which is 2. So you can easily find out that TCD of L should be greater than 1 nanosecond from this. And similarly, you can find the maximum frequency, which is T clock should be greater than equal to TPD of R plus TPD of L plus T setup of R. So you can say that T clock is basically greater than equal to, what is TPD? It is 3 plus 5 plus setup time, so it is greater than 10. Okay, this gives you the greatest clock period, or the maximum frequency, in other words. So this is just the summary of what we have studied. We have studied basically the design of how to design D latch and D flip-flop, and then we talked about the dynamic discipline or timing constraint. Then we covered the RTL model, single clock RTL model, and we will come to this other topic, which is also a very interesting one, of finite state machine, in the upcoming lectures. So with this, this is enough for this lecture. We will continue with the next topics.